Good day, everyone. Welcome to Super November AstroChats. Our Super November AstroChats will run in 2 Fridays of November, today and next week, November 13, 2020. To formally start our program, we'll proceed with the doxology performed by the RTU Himig Rizalia and to be followed by the singing of the Philippine National Anthem.
Mga kababayan, ang pambansang awit ng Pilipinas. Kayang magiliw, dalas ng sinakanan, alam ng puso, sa dikit mo'y buhay. Upang hinirang, kuya ka ng magiting, sa manlupin, di ka pasisingil, sa nagagang tutok sa simoy at sa langit mong pangaw, ay hinatang tulad, awit sa pagkayang minamahal. Ang isang ng matawad mo'y tagumpay na naghihingi, ang bituin at araw niya kailan naman. Araw ng walang pagsinta, langit sa piling mo. Ang ligaya ay mga amin, ang mamatay ng dahil sa'yo.
Again, good day, everyone. So, welcome to Super November Astro Chats. So, for today, our distinguished research persons are the researchers from the National Astronomical Research Institute of Thailand, or NARIT, the Rizal Technological University, Department of Earth and Space Sciences, and the National Astronomical Research Institute of Thailand has distinct and enormous partnerships since 2015. This year, we celebrate with NARIT as it marks our 5 years of cooperative relationships with them. We have started the Astronomy and Astrophysics Data Research Analytics Workshop, or ANA DRAW, which was held last August 2018, and a series of international workshops being hosted by NARIT to our faculty and student training programs. So stay tuned as we unravel the next partnerships with NARIT as we explore the anthropological practices and traditions of astronomy of indigenous groups as we prepare our next project for ethnoastronomy workshop. Moreover, this event is being co-sponsored by the International Astronomical Union Office of Astronomy for Development. We hope that you stay with us throughout this special two-part event brought to you by the Rizal Technological University and the National Astronomical Research Institute of Thailand. So to formally start our program, let us welcome this program that we may call on the very enthusiastic and supportive Vice President for Research and Extension Services of Rizal Technological University, Dr. Julius L. Meneses.
To our resource speaker for today's activity, Dr. Yutani Sawangwi, our friends from the National Astronomical Research Institute of Thailand, from NARIT, to our participants, friends colleagues in the teaching profession, and astronomical enthusiasts. A pleasant morning to everybody. In the past few years, the Philippines has been gradually developing its research and educational capabilities in astronomy. The development of astronomy education is still lagging behind several neighboring Southeast Asian countries, such as in Indonesia, in Thailand, and Malaysia, while it is advanced concerning several others. One of the main issues hampering the progress is the scarcity of trained professional Filipino astronomers and long-term visions for astronomy development. That is why I'm very thankful that astronomy has been part of the university's academic programs. The realization of such is a key in progressing astronomical concepts, ideas that could have adverse effects on our daily lives. I commend the organizers of this event, the Center for Astronomy Research and Development, headed by the R&D Director, Professor Ryan Manuel Guido, and with the leadership of Professor Guido as the R&D Director, I am sure that we will have significant milestones in the university's research undertakings. And for sure, astronomy will be part and parcel of these research undertakings. And I'm excited to have more and more research activities in this field. I'm also looking forward to what card could contribute more to the university's quest for excellence in research that would help the university and the country. Also, I am glad that we continue to conduct this noteworthy activity such as this despite these challenging times. We also thank the National Astronomical Research Institute of Thailand for being our partners in promoting astronomy to reach out to the students and community to proliferate science and astronomy. I hope that what you could learn this morning will ignite your passion for searching for what astronomy education can bring you. So sit back, relax, and enjoy the rest of the activity. Magandang umaga at God bless us all.
Thank you so much, Dr. Meneses, for the very wonderful remarks. It is indeed a challenge for the astronomy community to be part of this program. So, to continue, may we call on Dr. Tain Sarangwit to deliver the inspirational message.
Thank you very much for your kind invitation for me to join on your event. I hope you all can hear me clearly. So again, good morning here from Thailand, Narit, Chiang Mai, and I'm very happy to be part of our of your activity here. So for my part here, we'll be talking to you later on in terms of cosmology and how and what we learn about the universe. So from my side here, I would like to stress and take this opportunity to speak to many of our audiences in terms of what is the best time for us to be doing science, technology, mathematics, given the current situation that you see around us. Humanity is ever facing with a challenge, greater and greater challenge, as you see, that with the global warming, with the pandemic, and various other problems, the food security and so on. So it's the greatest time ever that we would need to have the knowledge of scientific research, technology development, skill in analytics, to come together to solve this problem. The problem itself is not going to go away. We have to come together, and there's no particular country or group of person can do this all alone. We are facing with a great challenge where we together as humanity need to work together. And having said this, although we'll be focusing on cosmology and astronomy, but it's very self-evident that many of the problems, many of the issues are not, can be solved by physics alone. You need the multidisciplinary coming together of ideas. Scientists come up with the critical analytics to solve the problem. And so we facing with great challenge, but at the same time, do not be despair. We also equipped with the greatest technological advancement ever. During our generation, there has been many new developments, the exponential increase in our advancement in technology. Now it's up to us to select, to use those technology, come up with the application when we can use them to solve our problem. And many of these will take years, and not just our generation. That will take the younger generation, our brothers and sisters, the younger generation, our children, our grandchildren. And it's really a good time where we are setting the example for years to come. With this, again, with the current situation and problem closer to home, let's say, closer to us on Earth here, we are ever facing with this problem and try to solve them. And I have no doubt that humanity shall prevail. So we've faced with many challenges before in the past, but I think people coming together will definitely solve the problem. And again, looking back here at the current situation, with this global pandemic of COVID-19, we have seen that now tens of billions of people have contracted the virus. No doubt that many more are affected by this, even if you're not contracted them directly, your friend, your relative, and also more than million people who have died from this disease already. It's just gone to show that not just physical science, biological science, healthcare system, and a lot of things that will need to be looked at. And this is the best time ever to do that. It takes some slowing down. We are moving at a very fast pace. Many people have been affected by this, but still, I think it's time. This slowing down is probably give us opportunity to kind of look back into ourselves, okay, and rearrange ourselves, reorient ourselves in terms of how we approach things. You may have heard a lot about people talking about deglobalization, decoupling. I think this is not such a bad thing. We have to be further apart. As we see now, international travel is almost impossible in many areas, including our own ASEAN nations. This would be temporary, of course. The decoupling, again, give us a pause and opportunity to rethink many things. Although we cannot, be traveling to see each other, but I think our connections as people, as human, is ever strong, and it's actually tell us what we actually need in life. We need each other companies, and many things, that we think it's not possible before, reducing travel and so on, with the pollution and so on. This is just...
Pangit tong Realme na to pagdating sa ano.
Hello? Okay.
Yes, sir, continue.
I'm not sure, maybe just nothing related, so I continue. Again, so this is a greatest chance ever. Do not be despaired by this. The declustering or the globalization or decoupling, although happened at the global level, I think at the regional level, it's telling us that we need each other more than ever. Okay, and with facing with this, and again, I express my confidence that we will prevail and we will move on ever stronger, equipped with even better understanding of ourselves and how we conduct ourselves as a race as humanity. And then hopefully we then can go back and focus on another kind of task at hand. I think humans has for a very long time have exploring spirit within ourselves. We see that from historical record, and even now, even with all this traveling between different continents become ever more convenient, and the time between this travel even cut short by our technological advancement. We as humanity, we look toward greater expand beyond our own Earth. And so I come back a little bit to touch on the space exploration, the scientific exploration of what is out there beyond our border of Earth, which is very important in its own right, that is ever reminding us how fragile the Earth is. Many of us have seen the pictures taken from space, seeing how thin and how fragile our atmosphere can be. And the more we explore and observe out to different, let's say, star system, we're looking for exoplanets, we're looking for any evidence that could indicate there's any life being developed on that planet, or there's environment that could support life. It starts to become clear that, and it's pointing back to what in science we do not like to believe that we live in a special place. There could be other worlds that exist just like ours. But as you know, the more you explore out, it's become pretty obvious that even though the chance of having another world similar to us is not zero, but again, it's still very small. So our own place here, our own Earth, is one of the very special place. If you were not too careful about how we live here to protect our Earth, our environment, well-being, it means that it will affect us eventually. And there's no other place where we can go. There's no other home. This is it. This is our home. Our current propulsion technology won't get us to anywhere where we need to go to find a new home for a very long time, certainly more than a century ahead. So again, this is come back to put a stress on why we need to really preserve our own precious home here on Earth, and we cannot do all this alone. Every nations, every nationality, every race has to come together to work on this, and in the meanwhile, our advancement in technology ever making our life even more convenient. The technology that we have, 4G, and now going up to 5G, we can order some things from across the country, across the continent. It's self-evident that with all this COVID lockdown, none of us having to kind of go back and live like a primitive time, back to the like Stone Age or Bronze Age, because we have all this technology that help us to actually make our living life quality that we all have. And again, just talking to our upcoming, our current generations, the student who may be in the audience, although we are talking about science, scientific research, things that we know about astronomy, about cosmology, as you will see, and you probably haven't heard much about it, is basically a stark reminder of how small, how insignificant we are in this whole expanse. And it's ever increasingly reminding us of although we have differences between different creed, different religion, different nationality, different race, but this is all we have. This is our brother, sister on this little blue planet, that we need each other together in this long endeavor toward millennia to come. Okay, so this ever telling us that we are all in this together, and so it's my belief that with our knowledge of the universe, seeing that how we actually need each other, will one day lead to our strong effort together to address the problem that I mentioned earlier, the food shortage, the global warming, and various other security risks that we face with different nations and so on. And finally, we can actually coexist in peace and working together toward a greater good of all of us. And it's my hope, sincere hope, that even during my lifetime, within I don't know how long I will live, we should live to see that where many of the nations working together on the space exploration, and we get to explore the space, using the space together for peaceful means and for the betterment of ourselves as a race, for humanity. And so yeah, so anyone who interested in studying science, mathematics, engineering, I think this is the best time ever that you will get a chance to use your skill, your knowledge to address many of the problems and use it to make a better living for all of us. So with that, I would like to end this message that would like to encourage many of you. Of course, many of you after listening to this might not end up studying astronomy. I don't want you to all to study astronomy. Otherwise, when we have to face with the next pandemic, we will not have excellent medical professor. We don't have excellent virologists to help us solve these problems. So we all need diverse a group of scientific mind. I express scientific mind. You could be engineer, you could be medical doctors, but with your scientific mind, working together on whatever the problem at hand and solving them. That's the most important. So with that note, I would like to thank you all for participating in this event, and I would like to return to the floor to the chairman. Thank you.
Thank you, Dr. Sawangwik, for a very moving message. We are with you that COVID should not be a hindrance for us to pursue engagement in the field of astronomy. And also, we are hoping that someday there could be a field like medical astronomy or space medicine. Before for that, we would like to acknowledge the presence of the Dean of the College of Engineering, Architecture, and Technology of Rizal Technological University, Dr. Noel Hugo Binag. Good morning, sir. And also, we would like to acknowledge the presence of Dr. Puji Irawati and Ms. Sulisa from the National Astronomical Research Institute of Thailand, and Ms. Abigail Mendoza from the Office of the Director for Extension and Community Services Center of Rizal Technological University. So now, for us to know more about our resource person's background and endeavors, may we call on Mr. Jason Calao to introduce our speaker.
Thank you, Professor Ryan. Good morning, everyone. Sawadee Kap. Our resource person for today is a homegrown researcher at the National Astronomical Research Institute of Thailand. He is an active member of the International Astronomical Union, where he is currently affiliated to several divisions. He specializes on extensive research of cosmology, large-scale structure of the universe, cosmic microwave background, gravitational weak lensing, galaxy formation and evolution, and alternative gravity theories. Ladies and gentlemen, we are pleased to welcome, live from Chiang Mai, Thailand, Dr. Yutain Sawangpit.
Dr. Songwit, you may now share your screen.
Okay. Yes. Okay. So to the screen share. Okay. So do you see my screen now, or is it as quick? Okay, let's you can see that now. Right. Okay. Okay. So you see my screen with the slide? Hopefully. Okay. All right. You all see my screen of this slide? Yes.
Yes,
Yes,
sir.
sir.
Okay. Very good. Okay. Again, thank you very much for a kind introduction. So and again, for this opportunity to be presenting to you and to share my experience and telling you, hopefully, like a telling story of a field that I've been working on for a while, and hopefully also share excitement of the knowledge of the current knowledge of the universe, and sharing with you how we get to learn about all these fascinating details back to the time when um, uh, comparing to the existence of humanity or the modern history that we have. These are way back to the really almost to the beginning of the universe, as you will see. Okay, so my kind of title or topic here will be on cosmology and the dark universe. When I say dark, I don't just mean that when you look up it's dark and just black, but you will see in a minute why we say that is really dark with various components that we have yet to understand. So the image in the background is what we call the Hubble Ultra Deep Field. It's very tiny piece of sky where if you look up, we just see nothing there, just a blank part of sky. There's no bright star there. Hubble Space Telescope been staring at this patch for a number of years. Each time you pass the part of the sky, it look at the sky, take an image, a short image, and it keep doing that for many times. And so when the scientists take the image and what we call stack them up or adding the signals, this is what they see or what we see. There's a huge number of varieties of galaxies here. You can see this is a tiny area. It's probably equivalent to if you were to hold up a pin. So this is like the size of the head of a tiny pin. If you hold up at arm's length on the sky, so really tiny. You can see there's a number of galaxies here. These are galaxies that you see. They have different shapes, sizes, colors. Sometimes we call the shapes morphology. So definitely they're telling us a whole lot about what is going on. And as it turns out, you can trace and study some of these galaxies back to the time when the universe is less than a billion years old. So currently the universe is something like 13, 14 billion years old. So you can look back at this back to really the early universe, and we can learn a whole lot and a great deal about it. So this just going to show that, okay, sorry. It's going to show that cosmology, what we study, because the light have a limited or limited speed. So it means that with this vast expand, when you look back, if you build a telescope to look to the light or pierce, look at the light that come from very far away, you also looking back in time. So in this case, you're looking back 10 billions of years, and you use this as a way to looking at different snapshots of the universe and how things progress. So again, I would like to take opportunity to introduce myself just a little bit. So this is me. I tend to think of myself as a cosmologist in the observational sense. So in astronomical sense, I do observations. I compare them to current theoretical background physics that we have. I also work in astrophysics as well. They can be a bit different. In astrophysics, we probably interested in what's happening with various systems. When in cosmology, we interested in the system as a whole and the collective properties of, let's say, some populations and stuff like that. So usually we tend to use, like, for example, this large kind of a telescope to observe or do what we call a survey. I will tell you a little bit more in terms of what we survey, to carry out a kind of galaxy, what we call cosmological galaxy redshift surveys, that we can learn a whole great deal about these objects. The image which I showed earlier, it showed different morphology, colors, but you can use what we call spectroscopy to study even further. You can look at what we call the redshift. So it's positioned in the space, so you can get a 3D position as well as that chemical composition. So that's a very valuable tool for astronomer to use. Okay, so usually you will need quite a big telescope to do this because you need to collect the light for some time, depending on the brightness of the object, can take up to an hour to what we call integrating the light together and send the light down the fiber, and the fiber gone down to what we call spectrograph, and then you get the data out. So a bit about myself. So this is another telescope that I spend a lot of time, a great deal of time using. This is a 3.9 meter telescope in Australia, in New South Wales. It's called the Australian Astronomical Telescope, or the AAT. It has the mirror of a 3.9 meter in diameter, but particularly the tool that I use is this, what we call the 2DF fiber and the spectrograph down here, that I use a lot. So for example, here you have the fibers, 400 fibers that can be rearranged within half an hour. So I have to stress that this is by no means something very simple. So you can see that there's a robotic arm here. So there are two sides of this instrument. I'm not sure if you can see my mouse or not, but I try to point the mouse here. So you have the two ends of the instrument. You can see that there's a black, like a black kind of tube here at the what we call the primary focus of the telescope. So while we are exposing one field, the other field can be rearranging the fiber ready for the next observation field, for example. And that can be, the turnaround time is about 30 minutes. So this robotic arm has to work really fast to place the fibers, 400 fibers accurately. I have to say accurately, because we're talking about a tiny different position and you won't get any light down the fiber. And the field of view, or the size that we can look at the sky in one of these pointing, is about 2 degrees on the sky. To give you a kind of size comparison, usually the full moon has the angular size of half a degree. So this is a huge, a big field that you can basically look at a particular part of sky for hours and get 300, 400 fiber spectrum of the objects. And then the fibers then feed down to this, the picture shown here on the lower right, what we call the spectrograph. Then it being split the light into the blue arms and the red arm. What the blue arm, the red arm is that the grating, the components, the CCD are kind of optimized for the UV part of the spectrum, and also the red part of the spectrum to get the base signal to noise out of this light. And yeah, that's me. Happen to be in that room when things broken down, when things are operational. Usually you don't get to go in there to see how things work, and so it happened when they were maintaining it. I got to go down, which is quite an experience. Okay, so with this kind of data, it's good. You spend a number of nights, sometimes weeks, to collect a lot of data, and hopefully the weather is good enough, and you don't lose. You get all the data you need. But most of the time, I also use what we call the data mining. This will be very important in the next topic that we will talk about with the requirement of the new generation of scientists or researchers with the data science. So in terms of data mining, there are already a good archive data, particularly during our generation. I think starting from year 2000, there's this Sloan Digital Sky Surveys. It started from like year 2000, so now it's like it's been going on for 20 years now. The data archive is huge. For example, here you can see that this is the plot of the a 2D plot onto the surface of the sky of the position of the galaxies. On the right, on the bottom, you can see that this is a picture of the telescope itself and the CCD camera with their filters that enable it to scan the sky on the big area and can do a large survey very quickly. You can see the distribution of the objects on the sky there and the footprint of the survey itself. Apart from using the kind of galaxy surveys, I myself also look at what we call the cosmic background. I'll tell you a little bit more in detail of what this is to kind of study the universe. This would give you really a signal that go far back, almost to the beginning of the universe. The light that this is coming from is the oldest, what we call the oldest light in the universe, when the universe was only 400,000 years old. So compared to the current age, this is basically a baby snapshot, baby picture snapshot of the universe. Okay, so with these kind of data, we'll see that normally it tends to require these kind of the space telescope. In this case, the one on the left with this gold kind of heat shield, that's the WMAP, which launched at around year 2000. And on the right-hand side is the Planck satellite, which go up somewhat 10 years later and regionalize a lot of our understanding of the universe, as you will see. So most of the time, I don't study them as a separate things. You can use the CMB. So you can see here on the left, this is CMB, what we call the cosmic background, as is streaming towards us. In the middle, it has to interact with galaxies and large-scale structures and gas along the way. With that, you can also use the interaction between the CMB and large-scale structure in terms of gravity, or with the hot plasma in galaxy clusters to study various different phenomena. In this case, what we call the integrated Sartre effect, which provide what we call dynamical evidence of dark energy. Okay, so I already mentioned a bit in terms of dark energy. So what I like to say here is that the universe is a dark, and dark place. And I didn't just mean that because when you stare out, it's just, dark of the night sky. But what I really mean by that is if you look at all these components or the makeup of the universe in terms of the matter and energy, we only know about or have a good understanding of the universe only about 4.9% of the whole, let's say, matter and energy budget. There's another 95% that we know nothing about. We need them in order to make our current understanding, our model, our physics work with our observations. To reconcile the theory with observations, we need what we call the dark matter and dark energy. Okay, so without these, you cannot reconcile our current understanding of physics and observations. So really, we know only about this 5%. So all of these are made up of the stars, the light, the planets, you and me, okay, and the rest of them we just don't know. So that's why I say that this is a dark place, because basically we don't know what they are. If you don't know what they are, you just don't know how to deal with them, and how does that play a role in shaping our universe and future of the universe. So it's one of our current issues, standing issues that we need to study in the cosmology. Okay, so I put down kind of 3 things here. The current issues is that what is the underlying physical framework of the universe. So let's just say if the idea of dark matter and dark energy seem outlandish to you, no worries. For many physicists, this is also a lot of physicists also feel uncomfortable with the idea of dark matter and dark energy too. So what happened if, let's say, I mentioned earlier that to get our current physical theory work with observation, you need to invoke the dark matter and dark energy. What happens if this underlying physical framework is wrong? Okay, so that's that questions there as well that we also studying. Okay, and the second question is then, if let's say for now this is our best answer or our best case, best theory to explain the universe is correct, then what is this dark energy and dark matter? So this has been a current theme of research for I think the past few decades. Apart from that, once we know all the underlying physics and the components, and then the questions of we look around us, we see all these what we call large scale structures, the galaxies, the galaxy clusters, even cosmic war and so on. So we can see here in the pictures here summarizing what we think happened at different time. So the question is, how does this large-scale structures form and evolve. So this is also, I think I would say that these three are actually the kind of the current and the main themes of what we call the modern cosmical studies of our age. Okay, so or you could summarize in this sense. So I show you the picture here, looking kind of back from, let's say, on Earth here. You can see pictures on the lower left here as a telescope peering back into the universe for on Earth. Of course, you would recognize this. This would be Milky Way that you can see it as a patch of kind of white dot across the sky. So that's basically our own neighborhood here in our own local galaxies, and you look through the plane of this Milky Way. So these are stars in our galaxies. Once you look beyond that, you see many of these galaxies. Again, these pictures are taken from like Hubble Ultra Deep Field that you saw earlier. We call this large scale structure, or LSS for short. And then as you look far enough, you start to come to the time when you start to see galaxies start to form. We call this the epoch of reionization, or EOR. Okay, reionization because before that the universe was hot and in the plasma state, and at one point the universe become cold enough, and you got the universe become what we call neutral because the electron and proton combine to give hydrogen. And then if you look further in the middle between the gap between EOR and CMB here between the yellow and the red line, you can see that there's almost nothing there. So it's an empty part of the sky. The time when maybe not even star even exist yet, no stars, no galaxies. We call this the cosmic dark age. So that's right after the CMB. I mentioned that the cosmic background happened. This is the surface where CMB is being emitted at around 300,000 years after the Big Bang. So between red line and yellow line, we think that this could last in order of 100 million years up to about 1,000 million or billion years, basically, where there's nothing happening. And then after that, things start to become interesting. The universe starts to become ionized. And then when you try to look beyond the CMB, this is all you can see. CMB is acting like the barrier, if you like, that the furthest distance, if you were to use the normal conventional electromagnetic means that we have to observe the universe, beyond that point, you cannot peer any deeper. It's probably similar to the photosphere of the star of our own sun. Beyond that, basically what we call the optical depth of the universe is too big. It means that the light that trying to come toward us just cannot come to us because it's trapped in this dense plasma. It's just scattered off from charged particle like electron and proton and so on. So the CMB would be, that's why I said it's the oldest light that we can peer back into. Okay, right. And also, I think we've probably seen many of these many times, these pictures that capture the kind of evolution of the universe. You probably start off from what we call the Big Bang, and then the universe expand very quickly in a very short space of time. We're talking about a tiny fraction of a second, and universe expand to 10 to many order of magnitude. We call inflation. And as you can see there, it's happened very quickly, and it's a very dense area. A lot of things, pretty much in theory, that we still need to prove with observations. And the CMB, again, you can see that this is a pattern of the green, yellow, and blue and red here. So that's the kind of or sometimes we call the afterglow light pattern. So this is CMB that we can see. After that, this is dark age. After that, you can see the structures, the first star form, and things evolve toward us. And this is where then we can study many of these galaxies, and then to push back, as I mentioned, like Hubble Ultra Deep Field, to look further back, deeper and deeper to galaxies, you need a larger and larger telescope, or you have to send things like space telescope, where you can get a kind of a darker sky, a more stable environment to observe with. Okay, so let's kind of start off from, let's say, what would happen. I mentioned earlier about the doing a survey of the sky in terms of the galaxies. So why do we do the cosmical galaxy survey? So like I mentioned, 90-something% what we call the dark matter and dark energy. Dark simply try to tell you that you cannot use a normal conventional mean to observe them. They emit no light, they have no interaction with light. We can infer their presence from gravity only. So to be able to study them, we use what we call the light tracer. Okay, so this tracer acting like beacons, so the galaxy acting as beacons. So to give you some kind of analogy here, which I like to use very often, is that, for example, here is the image or the picture taken from space by, I suppose, from a satellite on the night side of the Earth. And you can see that in this case, of course, you cannot see directly because it's dark, but you can see that where there's a city or people live, there are light, and you can trace out a major city, you can trace out a coastline. In this case, if I were to ask you, what do you think this is, which part of the Earth this is, with combining with your geography knowledge, you probably confidently would tell me that this is Japan, this is the island of Japan, there's a Korean Peninsula here, and you might even can tell me with confidence that this is Seoul here with a bright spot, and there's a clear, definite kind of borders here between the north and the south, and you can see the coastline here of China and so on. So with this, a kind of a similar analogy that we use the light that we can see to trace where things are or where matter or mass are. Okay, and so this is very important. Okay, so this is kind of the same technique we use, and this is when we say a universe of galaxies. Again, you can look at these various different morphologies. So these are kind of postage stamp cut out from Sloan. Now we probably catalog something like 100 billion of galaxies that we can see now with our ever more advanced telescope. And you can see the varieties and the colors, the shape, and so on. These are telling us a very interesting story about different evolutionary paths of different galaxies. And of course, this another puzzle that we have to solve, how they can have these all diverse and what their story is. Okay, so we can study a lot from even looking at these the colors and the shapes and how they evolve. Okay, so let's see. So for example, I'll show you here is a fly through, let's say, a video of kind of a galaxy redshift, what we call redshift survey. So when you do when you take a picture of the sky, you've got the 2D position of these galaxies, where they are in the sky in terms of the altitude or the east and west and north and south direction. But to get the full position, we do the spectroscopic survey, so you get the 3 dimension. Okay, so this is one of the survey carried out at the Australian telescope that we see earlier. So normally when we do the survey, because it's quite taking quite a long time, so you can see that that's why it looks like a wedge here. At the tip of the wedge, that's us. Okay, so we observe out. The more we look through, you basically look into larger and larger volume of the space. In this case, you can see that we are flying through some of these galaxies, and you can see different morphologies. These are taken from the real image, of course. Because I leave you some moment here to enjoy the view, let's just say. Okay, so that was the kind of animation made from the survey data. And you can see all these different colors and morphology, and the way they arrange themselves are not random. They have a particular structure about it. Okay, so this definitely not random, and we can say something about that. Okay, okay, this doesn't play. I will show you about our what we call the Millennium Simulation, but don't worry about that. So just move on. Okay, so right around the time of the year 2000, there are many of these Millennium projects. The computing powers start to become quite powerful in cosmology. We have quite a good framework of theory, and we want to know if you were to apply that. And let's just say you start off from what the word I like to say is that growing a universe in a lab or in a computer in this case. So you run the so-called like in-body simulations, and you put in a particle. In this case, we assume them to be dark matter particle. We don't know what they actually are, but given the observational property of this dark matter, we put them in the simulation and see how that how they would evolve in terms of structures, and how whether they can give us something that look resemblance to what we see from the current universe, from the nearby universe, for example. So this is the Millennium simulation. So you can see going from left to right is the time evolved. So we start off from something like in the top left corner here, things tend to almost look smooth, but you can probably pick out a small, tiny fluctuation in the matter. And as we go in time, you start to see that these structures start to become, or the contrast of these structures start to become larger and larger, and you can pick up from this structure very, very easily. And you can see some of these from the tiny kind of seed. Let's say these are seed that provided by what we call from the inflation, from the quantum fluctuation during the inflation time, start to grow into like a cluster size, and you can see there's a mark of the scale here. So there's a bit of a zoom in. So if you zoom in, so these are going from top to bottom. So you zoom into some of these structures, and you can see that how this structure grows. And this would be similar to what we expect from Milky Way, for example. So Milky Way would be living or residing in a similar region. So this would be what we call dark matter simulations, and that define the dark matter halo. And we believe that the galaxies are formed within this dark matter halo. Dark matter halo provide this gravitational potential well where the gas can fall into and start to form stars and galaxies. So again, we said that we want to run simulations and see how that compares to the real universe. And here it is. On the right-hand side here, from what we call the Big Bang to the big data, is that Big Bang, you run all the simulation with computational power that you have. And now when you carry out the galaxy survey, like similar to what I showed you earlier. So the bottom bits here, the one that plot in red, each of these dots is basically a position of galaxies in the 3 dimensions. So basically, it is a projection that you cut a thin slice of the sky, and then you project into. So going into from the center toward the outside, that's going deeper into the universe, or sometimes we call the look back time, or sometimes we parameterize this as the redshift here. So you can see that there's these dots. You can see that how they arrange together. We call them these are clustered. So they're not randomly distributed. Sometimes we see something strange, right? In the top part here, the blue dot, these are all data. So from real observations, okay? The earlier observations tend to cannot go very deep. So you see some strange structure. In this case, it's called the stick man here. So if you were to look out and see this, you will start to think that there's something going on here. But as you explore the volume of the universe out further and further, you start to see more and more of this pattern being repeated. So there's nothing wrong with it. So they just basically you're not observing the volume large enough, and once you do that, you realize this is a normal occurrence. And again, looking at these patterns compared to simulation, they look very similar, and that's kind of so these are kind of the first order look by eye. But in fact, astrophysicists or cosmologists, we use other statistical tools in order to actually compare in detail. But this can give you kind of a visual impression of what is going on from these millennium simulations to the from the data or from the real observations here. That this is quite an impressive framework of theory, and our current framework of our understanding can explain so much of what is going on with the observations. So as I mentioned, this gives you a nice visual impression, but when we actually look at things in detail, we look at their statistical property with what we call the power spectrum. So what power spectrum is that if you, again, look at this picture, you can see the fluctuation or the clustering at different scales. You can see maybe something happen at a very tiny scale, and then there's maybe correlation, what we call the correlation. If things happen in random, there's no correlation, right? So you wouldn't expect to have any correlation, but when you do, in such a case, you have a correlation even on the larger scale. You can see that there's a cluster here and there's a cluster here. They do not happen in random, okay? And the way to prove that is to use this, we call the two-point statistic, to study this in detail. So this is in what we call the Fourier space, okay? So with the higher k, or the wave number, is the smaller scales, and then on the left-hand side with the smaller k, or the smaller wave number, is the large scale. So we look at how things correlate together at different scales, okay? And this is what we found from different data. So for example, from galaxy survey like Sloan, you can see here in green. And from cosmic background, you see, you can pick out those hot and cold spots that give you correlation, and that give you at the largest scale possible here. So on the left-hand side, and you have various other traits as well, like galaxy clusters, galaxies kind of weak lensing. Okay, so that's give you all this, and then the red line here that you can see going through all this data is our current model of the universe, or what we tend to call the lambda CDM, lambda being the dark energy, and the CDM is what we call the cold dark matter, like that pi I showed earlier, right? So give us that kind of components and apply together with our current understanding of physics, with the general relativity and so on, give you this. So this red line is a proof that our current model fitting or going through all this data pretty well, okay? And of course, these are coming from like early 2000s. It means that now the data are getting even better, the error bar getting smaller, so you can pin down this red line to a very more precise. Okay, so again, come back to these pictures. We starting off from, we're seeing all these galaxies nearby to us, and we ask the questions, how these galaxies, how these structures come to be. And okay, we have this physics. Let's just assume for now, we don't know is the final solution, final theory, but assume for now, with the power of computation, you generate the simulation all the way from what you think happened right here, all the way here, and that's what you see. And now we can try to, let's say, go back to study the earliest signal that we can, so it's the CMB. So let's now look at the CMB, or the so-called the cosmic microwave background, a little bit, and what they are. Okay, so these are basically the heat relic. Okay, so it has been predicted, in fact, from the early 1940, since the time when Edwin Hubble detect the expansion of the universe. So by expanding, it inferred that at some point it must be coming together in a small point, small and dense. So it must be very hot, right? From maybe some high school experiment, you might have like a syringe with gas, and as you try to compress that, you touch on the container side, you feel that it's become warmer. It's the same thing, right? So things would be much hotter during the early time. So people, well, not people, but I mean scientists at the time predict that these kind of heat relic signal would still be around, and that would be in the spectrum of the microwave. Given the evolution of the universe now, we can predict the temperature at the time, okay, in order to fix various different, let's say, abundance or the number of elements that we have, or we see, or we observe in the star. like hydrogen versus helium, okay, because the what we call the primordial abundance of the elements in the early universe is mostly hydrogen with a slight trace of helium and lithium. Okay, so with that, we can predict what should the temperature be in order to build that much helium, for example. Okay, so people have predict the kind of the CMB and also predict what kind of temperature it would be. Okay, and as it happened, this group of scientists were building. So these are the group of scientists at Princeton, USA, try to build observation array or instrument to measure this cosmic background, but they never actually detected. And as it turned out, in around 1964, 1965, two engineers, Penzias and Wilson, detect, well, not detect, what they call is excess of the antenna temperature. They try to carry out, they were at Bell's lab, so they're using the microwave horn feed, like this one, to send a signal to communication with satellite and then bounce the signal from satellite to another Earth station. And so what they're interested in is to kind of try to get the best signal possible. So they do all they can, optimize to get the best signal, clear up all the noise. And as they were doing that, they realized that no matter how well they do it, there's still this kind of faint grow, faint signal, faint noise that always there, no matter what they do. They measure the strength of the signal in terms of temperature, okay? And so with this microwave signal in tens of gigahertz, basically, they can measure this temperature at around, I think you can see here, around 3.5 kelvins, okay? Whereas this group of theorists predict earlier at around 5 Kelvin. Kelvin is slightly different from Celsius, as you probably know, that 0 Kelvin meaning that it's actually the real absolute temperature, absolute zero temperature, whereas 0 degrees Celsius is not, okay? So, but the number at the time was still kind of approximated because people with nuclear physics and so on, the knowledge is not that kind of precise yet. So the calculation places it at around 5 Kelvin and the detected signal at around 3.5 Kelvin. The agreement of this number become better as the knowledge of nuclear physics become better and our measurement is better. And these two, being engineers, they discovered this by chance, okay? By chance, but no accident, because they were working very hard to get down to the signal. They were very observing. They were very diligent in what they were doing. So in fact, these two discovered, don't know what they are, send a signal for the physicists, for scientists to interpret. The scientists basically jump up and down. You discover the signal we've been looking for, the CMB. Okay, and comes 1978, these two won the Nobel Prize, whereas the those physicists who offer the explanation or the intuition, well, I wouldn't say did not won anything, they won something, but just not the Nobel Prize. Okay, so what this CMB is sometimes we call this a last scattering surface in the CMB here. So it means that beyond this point, the universe was very hot. So all the gas, all the matter that we have are in the what we call the plasma state. So you have electron and proton, basically. So these are all charged particles. It means that any light that coming, let's say from Big Bang, coming want to stream toward us will not be possible. They all got trapped in here up to the point where the universe expand more and more and cool down enough that electron and proton can combine to keep hydrogen. Once that happens, the universe becomes what we say neutral. So the photon can then stream through toward us. So this is a similar kind of analogy would be like this. You have a cloud here, for example. You look up, you only see the surface of the cloud. You cannot look beyond that, but it doesn't mean there's nothing beyond that. This microwave background is actually what you would see if you using a TV set and you tune to the channel where there's no strong reception, and you can see all this kind of background noise. This is pretty much what you actually see. So you can pick up or observe it with your TV set actually. So in terms of observation, as I mentioned, they see this as noise. at around 3 Kelvin. The physical kind of expectation at the time using what we call the Big Bang frequencies is expected at 5 Kelvin. But at that time, this frequency was just due to inaccuracy in our understanding of nuclear physics. After that, things get better. And people then, you can see here, if we were to plot spectrum of this radiation, it turned out to be very close, very one of the perfect black body spectrum, telling us that it's truly a signal coming from the beginning of the universe. It means that they are coming from a source that are well in what we call the thermal equilibrium. This means that this is not some kind of signal coming from our own galaxies or something in the foreground, non-primordial. Okay, so this you can see here, the peak here is at around 100 gigahertz. So that's why we call these microwave to distinguish microwave and radio. Usually radio tend to operate at around below gigahertz or maybe slightly lower gigahertz, but anything kind of beyond 10 gigahertz, we tend to call that microwave, but basically they are kind of similar things. They're still kind of a radio astronomy. Okay, so with that, this has been kind of basically put into, oh, okay, we found evidence of this Big Bang. So there must be this hot, dense beginning of the universe. And then the questions come with this primary fluctuation that the scientists, once we found this to be coming from, let's say, from the Big Bang, we theorized that at the time there should be some quantum fluctuation that would leave a signal that provide a seed to grow galaxy, for example, that we mentioned earlier. But we don't know for sure this fluctuation is at what level. So the scientists were set out to observe and make a measurement of this fluctuation level, which we have no clue about. And to measure that, is take a very sensitive instrument, and they keep doing that, but detect nothing. Okay, all the way at around 1990s, they start to see this primordial fluctuation at about 1 part in 100,000. So it means that the temperature of the CMB at around 2.7 Kelvin, you have to be able to build a detector that can measure temperature down to the level of micro Kelvin. Okay, so that's how hard it's going to be, and most time you have to send out a probe into space, okay, into a very stable conditions that you can measure this. So around 1990s, there's this space mission called COBE. In this case, COBE was orbiting around Earth and detect this both in terms of the precise measurement of this black body spectrum, as well as the first ever temperature fluctuation. So this temperature fluctuation you can see here is showing you the place where it's slightly hotter and slightly colder. But otherwise, what you would normally observe is just a kind of a flat spectrum like this. So this is what Penzias and Wilson would have seen with their horn antenna. It's just a uniform signal coming from all directions, except this is our galactic plane, of course, from the Milky Way. We have this additional contribution from our own Milky Way because of what we call the synchrotron emission, because there's a energetic electron charged particle moving in magnetic field, and also there's a dust, what we call dust, that absorb the starlight and re-emit in far infrared as well as microwave. Okay, so this is this is coming from our galaxy, but otherwise you get this uniform radiation coming from everywhere at the same flux or same temperature here. And then COBE going up 1990 start to detect this fluctuation. So once you subtract this average temperature, you do see this, and of course this is the galactic plane, our own Milky Way galactic plane. And then in 2000, this the next observation is what we call WMAP, the Wilkinson Microsoft and microwave and astroturfy probe that's been sent in by NASA. But this time, instead of orbiting around Earth, it's observing from what we call the Lagrange point L2, which something like 1.5 million kilometers from Earth. So it's even more challenging to do, but it will provide a more stable environment. So then we be able to then, with this, to probe even more sensitivity, we can detect or measure temperature to very high sensitivity and also a high resolution, as you can see here. So with this observation, it's been getting even better with Planck, which set up around year 2010, something like that. It was delayed a bit. So Planck, you can see here, compared to WMAP, you get very more sensitive, but at the same time, you get higher sensitivity. So you can trace out some of the last structure that you see here, but you can probe to even smaller structures here, and that really revolutionized our understanding of the universe. With those COBE results, two scientists or lead scientists that working on COBE got the Nobel Prize. One's John Mather and the other is George Smoot. One for measure of this perfect black body spectrum I mentioned earlier, and George Smoot for detecting that 1 part in 100,000 temperature fluctuation. And really CMB now going to what we call the precision science that we can do. So this has been hailed as a golden age of precision cosmology. Okay, so from these, for example, in the same patch of sky, you can see the resolution from COBE, you won't see anything. The map getting even better, and even Planck still improve that even further. So with this data, usually it's not doesn't just give you cosmology straight away. There's a lot of work involved in cleaning up what we call the foreground. So once you subtract the average temperature we talk about, there's this what we call the dipole component, which caused by our movement in the CMB field. So Earth and solar system and moving in Milky Way, and Milky Way moving with what we call the rest frame of galaxies. So you see this kind of dipole direction we're moving toward tend to look kind of hotter, direction we're moving away look somewhat colder. And once you remove that again, you got this, and then you clean the galactic plane out from here. You again extract something like what we call earlier the 2-point statistic. Okay, you see some of these hot and cold spots almost look like it's random, but actually it's not. So there's some kind of correlation between this hot spot and cold spot. So once you analyze them, you got again kind of power spectrum, but this time is in the 2 dimensions. So we call the spherical harmonics or angular power spectrum. So you can see that there's a perfectly a preferred scale here, a very high peak at around what we call the L multiple moment, about 200, or at about 1 degree. Okay, so you can see that there's a cold spot, hot spot here that actually have a preferred scale to be around each other at about 1 degree scale. Okay, so that's huge. Okay, again, compared to the size of the full moon at half a degree on the sky. And with this, astronomers, cosmologists were able to infer those these pies of energy contents of the universe, matter energy contents we saw earlier, about 4% being in the normal gas atoms that we know, and the rest of them, 90-something, 94, 95%, are made up of something we don't know what they are. And things getting even more fancier. You can combine various different observations to constrain some of these data, and you can see that we can try to study, like we see earlier, between normal matter, and this is what we call dark energy, and also try to study what this dark energy is by looking at what we call equation of state. Okay, so if they were to be around -1, that would mean it's what we call the Einstein cosmological constant. So that's why the game of try to measure the equation of state is very important for understanding dark energy. So this is again just to capture what the anisotropy would look like with the dipole at the level of 1 in 1,000. That depends on how fast we are moving in the rest frame of the universe, which turn out this contributes to something like 3 millikelvin. Okay, with this you can work out how fast we are moving in this space. So as it turns out, we're moving in direction of constellation Virgo, and so on and so forth. So with this, we can actually also learn about local dynamics of our local structures. And again, these are what we call the foreground. Okay, these are form planks. So as you can see, it observed not at just one waveband, it's observed at many different wavebands. The sweet spot for CMB, of course, is around 100 gigahertz, 120 something gigahertz here. But we go to lower frequency and higher frequency in order to address different foreground components. Okay, like I mentioned, there's a synchrotron emission, there's a dust emission, there's what we call the thermal dust here. So with this, you can constrain what this different foreground, and you try to extract only the CMB signal, which is the sign line here. And then again, this shows you how various of these different component affect you on the power spectrum that we saw earlier. So this is quite a challenging thing to analyze and require knowledge in mathematics, in computations, and so on to work. So in summary, what the CMB tells us is that this temperature is very uniform, where you see the fluctuation, it's only 1 part in 100,000. This is the light that coming from the universe when it was only just about 300, 400,000 years old. So very, very kind of early signal that we can try to study. And if we look at their nature, how they show us, is like I said, it's quite random in terms of temperature. If you were to plot like histogram of the temperature fluctuation, it's quite random, okay? But what I mentioned earlier, correlation, that's in terms of position. They are not random, but random in the sense that the temperature amplitude, basically. The spectrum that we see is not wide spectrum, okay? So you can see a preferred scale in the power spectrum. Statistically, they look isotropic in every direction, okay? So this is in fact, is how we study them from this. So you can write this in terms of like linear combination of different Fourier components. And with this, I just mentioned in passing, from this spectrum, you can learn a whole great deal about universe. The position of the first peak, for example, tell you that whether the universe is flat, open, or closed. The ratio between second and third peak, for example, tell you how much dark matter there is compared to normal matter. There's this very small scale we call still damping, and so on. If you were to have more neutrinos, more massive neutrinos, or warmer, we call warmer dark matter, you would have even stronger still damping, and so on. So this a lot of great deal we can learn from this CMB, as I mentioned. So CMB itself being close to inflation and the Big Bang, you can learn about how exactly what happened here. There's a lot of question mark here still, of course, with inflation, because it's very difficult. There's not a lot of observation done there. There's a neutrino, as I mentioned, as many of you might be surprised that normally you would heard about neutrino observation or experiment being done on Earth. But here with cosmology, you can use large scale structures and CMB to constrain the mass, the sum of the mass of neutrino, and also even the kind of number of relativistic species of these neutrinos. And of course, I mentioned already to study the dark energy, and also maybe to prove if the physical framework of general relativity itself is correct or not. Okay, so in fact, with this CMB, it's very remarkable things that we learn from it. Okay, so before the end, I mentioned a little bit just to kind of put in the last piece of the puzzle. All these galaxies that we see, we mentioned that they tend to look with have different colors, different morphologies, and what they mean. And even ourselves, we live in one of galaxies, galaxy Milky Way. How does that form and evolve? It's also one of the big questions. We see that the seed from the density, you have to start off from some kind of density perturbation. If everything were to be perfectly smooth, you wouldn't form anything, because gravity basically would be pulling you from all directions equally. So you don't have a collapsing of structures, so you don't form stars or galaxies. In this case, this density seed is provided from quantum fluctuation from the Big Bang, like we saw earlier. We saw the temperature fluctuation from the CMB at around 1 part in 100,000. Okay, so that was happening at the time, what we call the decoupling, or the last scattering surface, or if you consider it in redshift, about redshift of 1,000. Now we say that redshift is 0. And this value, the delta rho, the density perturbation now is roughly about 1. So given something like 13, 14 billion years, these structures evolve from density contrast. Let's say this is density contrast of 1 part in 100,000 to something like 1. Okay, so that's very fascinating, and how can we reconcile that? Okay, so this is one of the way that actually dark matter become even more important. Without dark matter, we found that you simply cannot grow the structure to have such temperature fluctuation that we see today, starting from the fluctuation that we see from CMB. So that's another kind of evidence requiring dark matter. And then there's another phenomenology which is very important. which I think maybe many of you also would be interested. As it turned out, we talk about black hole, and at a larger scale, we have what we call the supermassive black hole. Supermassive meaning that the mass of this black hole is in the order of millions of solar masses, all the way to something like a billion of solar masses, compared to, for example, a normal, what we call stellar mass black hole. When the stars, some of the massive star die, tend to leave these black holes, which normally the most massive one, maybe in order of tens of solar masses, which we see in the gravitational wave detection when they merge, for example. Milky Way, we found that, which is the subject of the this year Nobel Prize, of course. Milky Way itself has this supermassive black hole with a mass of, in fact, on this plot you can see Milky Way around here with a mass of something like 2 million solar masses. Okay, so what we found, or what astronomers found, is that there is a very tight correlation between mass of the black hole, and this is a sigma, what we call the reverse dispersion, which is an indicator of the mass of the galaxy. Okay, so this is somehow we found that there's a tight coupling between the mass of the supermassive black hole in the center of galaxies and the mass of galaxy itself. So you can see this as a kind of a snapshot. Okay, as the universe, as the galaxy grow from what we call merging, the black hole itself also grow from merging as well as accretion of gas. And so this basically telling you that the ratio of black hole mass and the galaxy mass always keep at this constant ratio, which is quite fascinating, particularly when you consider that usually black hole, we're talking, yes, massive, but they are very compact. Okay, whereas galaxy is on a huge scale. So to put things in perspective, if we were to, let's say that the size of the supermassive black hole is around the size of a coin, okay, and the size of the galaxy will then have to be something like the size of the Earth, right? So this is almost saying that something happened to Earth also affect whatever happened to this coin. Okay, so the size of the scale is a very big difference. Or vice versa, something happened to this coin is also affect what happened to Earth. Okay, so this is very very interesting and also very puzzling to astronomers. So this is one of the really important factor that shaping the evolution of the galaxies. Okay, so normally we say that the galaxy's evolution, and sometimes we call this AGN, or it's short for active galactic nuclei. So supermassive black hole by itself, if they are not in active state, so they don't create any gas, we don't observe them. So usually many of these tend to be in the active state, accreting gas and putting out a lot of radiation that we can see. And so usually we tend to be interested in the AGN phase of the galaxies. And this is a kind of summarized picture of how you would have the co-evolution between the supermassive black hole in the center and the galaxy itself, because you have this feedback process that basically the more you grow it, this feedback will basically stunt the growth of the galaxy, so preventing more stars from being formed, at the same time preventing the gas collapsing to feed AGN, or the supermassive black hole, even more. Okay, so this is kind of a scenario that the astronomers think give rise to all these different colors of galaxy, different morphology that we see today, that basically galaxy forming in different environment, massive environment versus low mass environment that give rise to this diversity. So the more massive, things happen very fast. Okay, so kind of live fast, die young, burn the gas up very quickly, and then end up as being the red and dead galaxy, early type galaxies, whereas the one that at the lower end didn't go through this phase, so still appear to us as these blue spiral galaxies and still forming stars today. I wonder if this will play again. Still a similar problem, but I think I have. Okay, maybe not. Okay, because it's share a different screen. It's okay. Okay, so maybe I just skip that. So what this is just that it's a simulation of two galaxies being merged. Okay, once they merge, the cold gas got disrupted and feed to the central supermassive black hole, which in turn power this feedback process and prevent further star formation and also gas to feed the center. But anyhow, I cannot show that now. Okay, so when we talk about this feedback process, there's a lot of evidence. For example, when you talk about, I said that two galaxy merge and two black holes, supermassive black hole, then would end up at the center of galaxy, and this is such evidence. So this, you can see these galaxies is like a train wreck, right? There's the morphology here. What we would call a regular galaxy because of the merging, disrupt, usual shape of it. And when we look at the center of this galaxy with X-ray, you see some faint glow here in X-ray because of the gas that's feeding this supermassive black hole will tend to emit in X-ray or UV. And here you see the two kind of bright sources at the center, which we believe to be the remnant of this merging. You have the two supermassive black hole that didn't quite merge yet, or maybe on the way to merging, but still give us this evidence that, in fact, yeah, you do see this actually happen. And it's not just a theoretical belief or expectation alone. And this is another good evidence of this feedback process. In optical here, you can see this is a large galaxy clusters. At the center, you have these elliptical massive galaxies that happen to have the supermassive black hole accrete in the past and shoot out this jet. Okay, so when you look in the radio, you can see there are two jets here that are coming out. And again, once you look in the X-ray light here, this is a hot gas in the center of galaxy clusters. This is what we call the intergalactic medium that collapsed due to the gravitational pull. And along the way, they got heat up because they go into the denser area and then ionized into plasma and then emitted X-ray as a way of cooling further. And as this jet was coming out, it's punched the way through. So you can see here, there's this dark patch, two holes here, one at the top and one at the bottom. And when you line up with this radio jet, you can see how perfectly they align. So in fact, we have many of these observational evidence to suggest that, in fact, the supermassive black hole or the agent are very well aligned with how the galaxy evolutions happen. So again, back to what I mentioned earlier about we living in Milky Way, and Milky Way itself is quite relatively low mass galaxies and didn't go through this phase of having the supermassive black hole very active and accreting gas and putting out many of this radiation that could harm the development of intelligence, life form. Okay, so this is again, just to put things in perspective, how spatial or how unique our position here could be. Okay, so again, just to capture all of that, this is what our current issues that we are facing. And astronomers now, and astronomy is similar to other scientific research, having to go through the paradigm shift. Okay, what this means is, in terms of paradigm shift, is that go far back a few centuries back, science, as well as astronomy, we are just some kind of empirical science. You just do experiment, you observe. You don't know what's going on. You just report the result, okay, and you maybe have some relation where you can predict what will happen next, but not the physical insight. Okay, probably pretty much like in astronomy, you would relate this to Kepler law. Okay, so that's purely empirical based. After a while, physical models start to catch up. When Newton, for example, discovered the law of gravity, then people start to understand how this Kepler law come about. Okay, and then fast forward to 1950, we cross into the third paradigm where we start to have a more powerful, we have computer, we have a powerful computational power, and we start to make our physical model become more complex, and you can solve them with computer, but not by human being. So that's what we see leading up to year 2000, where we see this millennium simulation, for example. And then now we really cross into the fourth paradigm shift, where the scientific research is now what we call data-driven science, where it's not all about you have a bigger telescope to get the data, or your theories come up with a brilliant theory, but rather there are huge load of this archive and data that you can study. And so we all heard of this area where you have combined computer skill, math, statistics, and your domain knowledge. Okay, this domain knowledge in this case is astronomy, but could be anything, right? And you end up with what we call the data science. And so maybe go back, I might sound a bit like old people here, go back like 5 or 10 years, people talk about researcher having to have this T-shape, one being the broad and then deep in your domain specialty. But now we talk about modern researcher having this pie shape. Okay, you need this statistical computing skill to go with it. Okay, in order to make things work or to make competitive research work. Okay, in astronomy, this going even beyond. So it's how does that apply? You probably have guessed because we have billions and billions of galaxies. Furthermore, we tend to employ multi-wavelength or multi-messenger astronomy, as you heard. We use radio, we use optical, we use X-ray, we use gamma ray, and now you have Persian wave, you have neutrino as well. So we are truly multi-wavelength, multi-messenger to study whatever phenomenology. For example, as example, we talked earlier is supermassive black hole agent. For example, you were to study an elephant by a group of blind men or women, let's say, each one touch on different bits of elephant would say that, oh, elephant look like different things, right? But you need all these blind men to kind of come together and actually arrive at to what actually the elephant looks like. Okay, so these are a kind of next data challenge that coming up during our time, if anyone interested. So a few last slide would just be me advertising a bit for people who are interested in this kind of research in astronomy. So again, astronomy will provide a way for you to train in this, and once you acquire this skill, it can be a transferable skill that maybe you will be highly sought of to work in business, work in industry, and so on. So this is what would happen next, right? In astronomy, this is actually nearly a completion. The LSST, Large Synoptic Survey Telescope, will produce huge a lot of data, 30 terabyte per night, which astronomers need to sift through, and billions of sources per night. We're not talking about after 10 years of survey. We're talking about one night, you have 1 billion sources object you have to go through. So these are truly kind of a big data science that you need to employ. And then again, you might have heard of this square kilometer array being built in Western Australia as well as in South Africa. That will produce an, I would say, ridiculously amount of data. We talk about 160 terabyte of data per second. So it means that you won't be able to store all of them. You have to analyze them in real time. So all those things you heard mentioned about, machine learning, deep learning, AI, you need to use all of them to select which bit of data is worthwhile for keeping and which one to chuck away. Okay, and with that amount of data to get any science done is great because you have lots and lots of data to back up your science. But again, you need to learn all these skills to actually properly bring out the power of such observation. So with this last slide, again, advertisement of what we are doing here at Madrid. There are already various different kind of projects that we're involving with international community in the survey and study of the universe from Persian wave, optical kind of counterpart surveys, all the way to the future gamma ray observations, the so-called Cherenkov telescope array. There's a neutrino observatory in southern China. There's a radio huge telescope here called FAST, and of course the SK itself, which I still put question mark here, whether we will get involved or not. But yeah, so many of these activities would be very interesting in nurture the next generation of scientists, data scientists, engineers, and technology developers. And so if you're interested in, do get in touch, and this would be a nice opportunity for all of us to work on this together. So with that, I thank you very much again to organizer for inviting me, and thank you for all participants that have been listening. Thank you.
Thank you, Dr. Yutain. I think Professor Guido is having some connectivity problems. For that,
Hello? Am I
I think,
clear?
yes. Yes, sir, you're here.
Okay, thank
Loud
you.
and clear, sir.
Sorry for the technical problem. Thank you, Dr. Sawangwit, for letting us explore and reveal the nature of our cosmos. You shared us to understand the universe that I know that through your talk, it also provide the non-astronomers, non-specialists, and the community the horizon of the fascinating and informative context of the universe. It is truly that learning and discovering new things allow us to continue traverse the path of success. With the help from the advent of emerging technologies, especially in the field of astronomy and space sciences, we eventually revealed the vastness of the universe. Before we proceed with the open forum, may we ask our students for their major takeaways in our Astro Chats. For the Master of Science in Astronomy students, may I call on Mr. Joshua Felizarta?
Good morning, everyone. Thank you very much, Dr. Sawangwit, for sharing your knowledge of our topic for today, which is cosmology. The talk clarifies my understanding about the cosmic background radiation, dark matter, and dark energy. This concept haunts me for a long time. However, the talk of Dr. Sawangwit shed light on this topic. I will not list down all my knowledge learned today, but trust me, I learned a lot. Instead, I will give my reflections to our talk for today. While listening to the talk, I reflect that human knowledge is incomplete. We taught humans that we know everything about our universe, but this is not the case. Our knowledge about universe is just more than 200 years old since Greek and Mesopotamians observed and recorded their knowledge about the night sky. Thus, humans should continue to pursue or do not stop learning by researching more about unknown knowledge like our universe. There are more treasures to unlock if we continue learning this knowledge. Also, human collaborations is very essential in achieving our goal of complete understanding of our universe. I would like to thank the National Astronomical Research Institute of Thailand and Rizal Technological University for continued collaboration in deepening our understanding about our universe. I look forward to this kind of talks in the future. Again, thank you very much po.
Okay, thank you, Joshua. We would like to say hi to your flamingo background. Okay, thank you. Now, maybe we can ask Miss Aki Nodado.
Hello, everyone. Good morning. First of all, I'd like to thank Dr. Sawangwit for his time and imparting us a concise knowledge about cosmology, specifically to the available telescopes for observing the observable universe up to the cosmic microwave background, which are essential to the study of cosmology. What really captured my attention is I've learned about the CMB dipole, which are moving in the direction of oscillation due to the CMB radiation, which is very interesting. Also, it also captured my attention about the uh, advances in science, especially to the paradigm shifts from empirical science up to the big data driven science, we can which can make us learn more about the universe that we are currently living in. Thank you.
Okay. Thank you, Joshua, and thank you, Aki. Now, let us hear from our BS Astronomy students. Let us hear from Mr. Alexander Monte.
Um, Good afternoon, everyone. Thank you to RTU AstroChat and to Mr. Yutain Samangwit. And I think learning cosmology at the very first year of the astronomy program, it really opened my mind into a very vast expansion, just like the universe. It visualized myself and us into a very small atom when I saw the map or the structure of the universe in the presentation lately, that where are we in that expand. It answered my question, and curiosity, how to how the expand affect us, especially the prolonged survival of humanity, that we have to put all aside of our political differences. The health and well-being of our planet is so much important than everything else. Thank you.
Thank you, Mr. Alexander. Uh, how about Mr. John Jasper Raquel? May we know your major takeaways for today? Wala kang audio.
Hello, so good morning, everyone. So, my major takeaways for this day are the following. So, I've learned that the universe is mostly dark, and we only know almost 5% of this universe. So, that's accurately 4.9%. And from this lecture, I have understood that there are certain problems that arose from understanding, especially the physical framework of the universe, and what really, uh, what really dark matter and dark energies is, and their purposes in understanding our universe, and currently explaining uh, what what's happening right now in the universe, and how does the large scale structure form and evolve, and what are the problems that arose from trying to understand the big data that we have, especially that the technological advances that we are undertaking, and especially what gives the most impression to me is the correlation between the mass of the supermassive black hole and its in its tight correlation with the uh, velocity dispersion. And that's all.
Okay, thank you, Jorn. And we would like to acknowledge the equations behind you. Okay,
Thank you, sir.
maybe we could have another one. Maybe we can have Miss Bea Kahandig.
Hi, good morning to all. This talk made me realize that cosmology is truly an interesting field. And my major takeaway for this from this webinar is that being in the third world country is not a hindrance in studying fields like astrophysics and cosmology, even though these fields are not as appreciated as other developments. And the data presented earlier were impressive. And if these works are really developed and studied well in even in countries like ours, these can be this data can compete in the global study of cosmology, and this can contribute in our gradual understanding of the universe. So, and I agree to what Dr. Sawangwit said, that modern researchers should be pie shaped instead of the usual T shaped researchers. And we are looking forward for more collaborations, research collaborations with NARIT. Thank you to the RTU card for this opportunity, and also to NARIT.
Okay, thank you, Bea. Thank you guys for sharing your takeaways. Now we can proceed with the open forum. Let us start with the questions from our Zoom chats. We have a question from Mr. Oriel Tumanan. Dr. Sawangwit, neutrinos do not, or at least weakly, interact with normal matter, and they are known to be very abundant in the universe. Is it possible that neutrino particles are dark matter? If so, how much of a dark matter they are? Thank you.
Mhm. Well, that's a very good question, actually, because that's one of the questions that scientists ask ourselves too. Okay, the point that you talk about is really spot on. Okay, neutrino being weakly interacting would be a perfect candidate. Okay, as it turned out, it cannot. If it were to be candidate, it cannot be the sole candidate of dark matter. Neutrino being very has a very low mass. Okay, it's from its oscillation we know that it has mass. Okay, it's not massless, but it's very low. So they behave almost like a photon, like radiation. So they are very we call relativistic. If we were to match with what we call dark matter, we tend to class them as the hot dark matter. Hot dark matter is being basically, low mass, highly energetic. I mean, scientists did some kind of simulations and calculation with hot dark matter, or things that would have similar property with hot dark matter. you basically will not form a structure that small enough to reconcile that with observations. So if you were to have neutrino as dark matter, you might be able to form very large galaxy cluster, but any structure at small scale, it will be basically impossible to form. Now, turn back to, can neutrino be a candidate or some part candidate? Yes, it's possible. That it could contribute to dark matter, but itself or dark matter itself cannot be solely be a neutrino, because otherwise you wouldn't get observations that we see today. So yeah, even the question of dark matter, it might not be just a single kind of particle. It could be a mixture of things, and at what proportion, that's really a field of active research.
Okay, thank you, sir. Another question from our astronomy student. What are your thoughts about the actions as the candidate explanation for the dark matter?
Sorry, what are the
Actions.
action?
AXIONS.
Oh, okay. The axion. Okay, sorry. So I know it's people can pronounce it very different. So okay, so I think what you talk about is the axion. Axion is one of quite interesting candidate right now. Okay, given I have to say that sorry that we only have 1 hour, so that's I think talk about dark matter could take up the whole another hour or two by its own. Traditionally, or even now, what we are doing with the particle detectors, or that we try to detect dark matter, is based on a model. We call that these dark matter are what we call the weakly interacting massive particle, or WIMPs. Okay, so massive particle being that they have a mass. I'm going to use a bit of a unit where it's quite specialized here. So they tend to have a mass of the order of, say, 10 of giga electron volt, okay, to like tera electron volt, for example. So they are very massive, and many of the experiment has done a lot of observations, and so far we not yet discover anything in that area, in the massive area. Okay, we still have many data, many observations, many years to go through, but indication right now is a bit scary that we start to running out of particle space in terms of the cross section versus mass, and we have not yet found anything. Right. So many scientists are now start to look for alternative. One good such candidate is axion. Okay. So what the difference between axion and weakly interacting massive particle? Axion can have a very small mass. Okay. But in itself, although small mass, unlike neutrino we talked earlier, it can be what we call non-relativistic. Okay, so the mass could be in the order of like electron volt or kilo electron volt, for example. Okay, so and it's arise from some of the particle physics model, which we require to explain some of the what we call the strong CP violation or lack thereof. I'm not going into detail on that, otherwise we'll be here all day. So in itself, it's quite a good candidate, and there's experiment that now being planned or underway that basically try to detect the light through the wall. Okay, so just going to go to this a little bit just to excite, if you haven't read about it already, just to excite you, is that axion has this special property that it can interact with a strong magnetic field and give off light. Okay, so in itself, of course, they are dark matter, so they're not supposed to have a lot of interaction with normal matter or light, but in itself, they can interact with magnetic field and give off the light, for example. So in that case, in terms of astronomical observation, we try to detect such a signal, whether we can see such light. I mentioned the SKA, square kilometer array. As it turned out, that light or that photon will have a peak in the radiation in the radio. So in the, if I remember correctly, in gigahertz or megahertz, something like that. So low frequency radio survey like SKA are also hoping to do that, to detect whether you can see evidence of axion, or on Earth in the lab, people can also try to basically use a light source, a very high intensity light source, dump into the wall. Okay, by dump, I mean they have a very strong magnetic field, which we can do because we have superconducting, we have all this technology like a particle accelerator and so on. So we can produce a strong magnetic field. You have a strong light source, dump and hit the wall basically, with magnetic field. And so what you hope to do is that you reverse the process. Okay, so you put a strong photon in with magnetic field, and you hope to produce axion. Okay, light cannot pass through the wall. Okay, which is opaque, but axion should be able to pass through the wall because they have a really low interaction. So on the other side of the wall, you try to convert that process. You have a strong magnetic field and looking to see if there's any light coming through. Okay, so if the axion coming through the wall interact with those magnetic field, then that it should give off photon. Okay, so the more photon you have on the other side, or the light particle, the chance of producing more axion, and the more axion you have crossing the wall, the more chance of producing the light that you can observe on the other side. So this is what we call the light through the wall experiment. This has been a serious consideration plan for future experiment, and some maybe like a prototype or proof of concept already underway for that. So yeah, so it's one of the very interesting candidates right now, considering WIMPs are running out of place too high from us, or we running out of place to look for them.
Okay, thank you, Dr. Songwit. There are plenty of questions in our Zoom chat, but due to the exigency of time, maybe we can accommodate last question from our Zoom chat. The last question is, what is your insight about the ultimate fate of the universe based on the current available data and observations that we have? The question is from Mr. Aldrin Gabuya, the resident astronomer of Al Sadim Observatory.
Okay, so if we can get the question again, what is
what is your insight about the ultimate fate of the universe based on the current available data and observations that we have?
Right. Okay. Again, good questions, and we like to know. Sadly, given usual lifespan of human being, we will not live to see it, but we can theorize about it. So based on, let's say, based on current knowledge and data, it has a very strong constraint on what we call the lambda CDM. Lambda being cosmological constant, there are many candidates that try to explain this accelerated expansion, but this is the leading candidate. And it is true that dark energy is the cosmic constant. It means that the universe will expand forever. Okay, so that might not be the future that I prefer or I like, but indication from many observations pointing toward that direction. So let's just say, okay, if it were to expand forever, what would happen then? What would be the fate? Okay, so the space would just keep expanding forever, meaning that we have a limited amount of gas, right, that make up stars, galaxies. So it means that these going to get more diluted. Okay, so as you would have, right, a gas in a box, you make the box even bigger, so the gas become more and more diluted. Gas become more and more diluted. It means that it will be harder to form stars. Okay, and the star that already come to the end of the life will die away. So ultimately, you can imagine, right, the universe would be dark, empty, cold place. Doesn't sound very appealing, but I can be sure that that would be, billions of years from now. You have nothing to worry about right now. So that would be kind of ultimate fate. And if it keep going long enough, a particle that usually are very stable, like proton, will start to decay. Okay, proton quite stable, but it has a half-life, or we'll talk about billions, billions of years. It means, but if you go that long, proton itself will start to decay. So if that's the case, our universe will turn into, a cold, dark, empty, boring place to be. And so that's not very appealing at all. But I'm afraid the current data and model pointing toward that direction.
Okay, thank you, sir. Maybe now we can accommodate last two questions from our Facebook page. May we call on Mr. Gian Santos to raise the questions to Dr. Suangwit.
Hello po, Sir Sawangwit. We have several questions po from our Facebook Live. Our first question is from Glenn Lang. The question is it true that the dark matter that we know is just information which has gravity? Again, the question is it true that the dark matter that we know is just information which has gravity?
Okay, let me just double check that I get the question right. The dark matter is just the information with gravity.
Yes, sir.
Okay. Not sure how to answer that. When you talk about information, there's many ways of looking at it, right? We look at this when we consider black hole, for example, of how, when things are created into black hole, whether information loss, and then you get into the arguments or this consideration of entropy. So what we're saying, trying to say that is perhaps like what we mean by information is this basically entropy. But then again, this information of entropy, how they interact with gravity would be interesting, right? Then you would, with a consistent kind of quantum field theory of how these things interact. Let's say with gravity, then usually it have to interact through gluon, for example. If I have to answer you right off now, I absolutely no idea, but otherwise could be one of the interesting thing to explore, particularly if you're a theorist. Sometimes this revolutionary idea come from things out of the box, very similar to what Stephen Hawking, for example, like I mentioned, right? Posing the same question with information or things that go into black hole and singularity, how whether it lost or not, or whether it reappear as the Hawking radiation and so on. So this is the questions that, yeah, you can pose the questions and you have to think about, okay, if you were to try to answer it, what sort of tool do you need, what type of thing you have to do. So this is interesting question, and I have to tell you, I have no answer for you, but only can offer that idea related to it, like I mentioned.
Okay, sir. The last question from our Facebook Live is, are observation data from NARIT Observatory available online for other researchers?
Mm-hmm. Yeah, we would like to make it available online. Currently, we have policy already that we would like to share. Usually, with the 2.4 meter, it's normally made into what we call the PI, the principal investigator who propose to use telescope. Once they get the data, they will have a year and a half to work on their scientific target or scientific aim of the proposal. After that year and a half, we will make the data public. Okay, so anyone basically can get their hands on them and do whatever, as long as, of course, if the science is exactly as the original owner of the data and that work has been published, then maybe you might be in trouble to try to publish the same thing. But if the original previous owner didn't publish in the same field, or you found something useful that is an add-on to that data, of course, that will be very welcome. So in that sense, it's like kind of value added for our data. So we want to do it. And policy is that currently we haven't got a channel to do that yet. We have a prototype where we want to work on have the data archive, public data archive, where anyone can get to the data. But of course, you have to be careful in terms of access of data. You have to check whether this person is the rightful owner or have permission to the data or not yet. So it's a more of the technical thing that we have to implement. But yeah, the willingness is there, the policy is there that we want to share. And actually, to mention it, that's probably another area. If anyone in the audience doing things like computer science and computer engineering would like to explore a project of that kind of area together, then yeah, you are more than welcome to talk to us and see if we can work together on that.
Thank you, sir. That's all for now.
Thank you.
Okay, thank you. It is a very engaging AstroChats that we have with Dr. Sawangwit. Okay, now to express our deepest appreciation to our resource person for today, we would like to call on Dr. Ruby Ann de la Cruz to award the virtual certificate.
Hello, good morning. The Center for Astronomy Research and Development, together with the Department of Science and Technology and the Rizal Technological University, presents this certificate of appreciation to Dr. Sangwangwit for imparting invaluable passion of scientific knowledge and development during the Super November AstroChats Cosmology held on November 6, 2020, signed by Associate Professor of the Center for Astronomy Research and Development.
Okay, thank you, Dr. De La Cruz. Now, for announcement, please be with us next week. We'll be having Dr. Puji Irawati from NARIP to share us her expertise about stellar evolution. So that's on November 13, 2020 at exactly 10 a.m. Philippine Standard Time. Then Dr. Ernest Makalalad will be chatting us about the science of space environments, also November 13, 2020 from 2 to 3 p.m. Then for 3 to 5 p.m., we will be having a special workshop exclusively for BS Astronomy students, also under Dr. Makalalad. Now, to continue to deliver the closing remarks, may we call on Dr. Catherine Tria, the university director for administrative services and the project management officer of the Center for Astronomy Research and Development.
Yes, hello. Good morning to everybody. Am I heard? Jason,
Yes,
can you
ma'am.
hear me? Okay. Yeah, so we would like to thank Dr. Yutani Sawangwit, a researcher from the NARIT, for the topic entitled Cosmology. And also, we would like to thank you, sir, for taking some time to actually participate in this talk, the AstroCHATS, as sponsored by the Rizal Technological University and the Center for Astronomy Research and Development. Sir, we would like to appreciate your effort and your time giving to us, and we hope to have you again soon. Again, Sir Yutani, thank you very much. And again, thank you for the Astro Chats, and we shall see you next time. Good afternoon.
Thank you, Dr. Tria. Before we end this program, may we request everyone to please turn on their cameras for us to have a group picture taking as a remembrance that we are all here together with Dr. Sawangwi. Okay, Sir Jason.
Okay, so I will take a screenshot for the first frame. Smile. One, two, three. Okay, for the next frame. Okay, smile. One, two, three. Okay, for the third frame. Okay, smile. One, two, three. Okay, so for the last frame. One, two, and three. Okay, thank you.
Okay, thank you so much. Thank you to everyone. Thank you to Dr. Sawangwit for this very informative and very engaging chats that we have today. Again, everyone, thank you so much. Goodbye.
Bye. Thank you.
Thank you. Bye.